Okay. Hi, everyone. Thanks, Alexa, for miming that to me. All right. Well, I thought I unmuted, but the mouse is funny. All right. Well, I'm going to start over. Hello and welcome, everyone. You are tuned into another Swift Industries live event. This is being recorded live April 22nd, 2021 from occupied land of the past, present, and future Duwamish Coast Salish people, currently known as Seattle, Washington. Tonight is the first of a 4-part series with science geek and cyclist Alexa Everson. My name is Jason. I'm the co-founder of Swift Industries and Swift Adventure Co. And tonight I will be your host. I will introduce Alexa in just a moment after I make a couple of quick announcements. Next Wednesday, April 28th, is the season finale of our Stoke Spoke Adventure series. Stoke Spoke is a community-driven route sharing and adventure presentation. You can check out the previous recordings from this year on our YouTube channel, and you can mark your calendars for next Wednesday evening at 5:30 Pacific time. If you plan on visiting the Pacific Northwest or you live in the Pacific Northwest, we have our sister company called Swift Adventure Co. And Swift Adventure Co. offers some pretty rad bicycle rentals for gravel and bike pack riding, as well as a number of guided bike trips and workshops. So go ahead and check that out. And with that, I'd like to introduce our guest for the evening. Alexa Everson is a Black woman, a Black fox, an outdoor recreationalist, a geology enthusiast, and a scientist of all trades. As an Enneagram Type 1 and Scorpio with Virgo rising, her nature is to learn through logic, patience, and reason. Whether it is route planning, advocating for BIPOC representation, guiding folks on tours, or simply cooking up something good, she treats all her interests like a science. In this fun and factual series presented by Swift Industries, Alexa will be sharing her scientific findings on various topics that folks of all experiences can enjoy. I'd like to welcome Alexa.
Hello.
Hi, Alexa. Thanks for being here tonight. I'm very excited to hear what you have to say about geology and riding on gravel.
Thanks. Thank you so much for that introduction. I'm really excited for this because I truly am a science geek about this kind of stuff. And yeah, just being able to share this information, hopefully a good balance of fun and factual. I don't want to get too bogged down on details because I know it can kind of go over folks' head. Folks are getting off work right now, just trying to enjoy their 5 o'clock beverage. So hopefully this is going to be simple enough, and we'll keep it fun and light for the most part. But yeah.
Awesome. Sounds great. I'm going to give you the screen.
All right.
If folks have questions, you can throw them in the chat. I'll keep track of them, and we will do a short Q&A at the end. I'll see you later, Alexa.
Thank you. Thank you all for being here. Hopefully this won't be too long because I really could talk forever about all of this. But we're going to try to keep it fun and factual and just let you know kind of the general idea of what geology is and how it applies to your time in the outdoors. So with that, first we're going to start off with talking about my background and what brings me to even talking about this kind of stuff. Most of you have probably just seen me on bikes or, you know, whatever, on Instagram, and sometimes you don't really know who people are. So I'm going to let you get to know a little bit more context as to why I'm doing this. My name is Alexa Everson. My pronouns are she, her. I am currently on the past, present, and future land of the Chumash, which is also known as Santa Barbara, California, which is on the central coast of California. Awesome, beautiful place. Happy to be here. I am wearing my geologist Hawaiian shirt because that's what they like to wear, and I'm also wearing my sun hat, just to be in the fun vibe and aesthetic of what geologists are typically considered to look like, but also how I like to look. Anyway, it's fun. I am an all-around cyclist, hiker. I'm a travel guide professionally. I'm a writer, and I'm an advocate with the Black Foxes, which is a collective of Black cyclists who are advocating for more and better representation of Black people within outdoor recreation and just encouraging them to get out there more. Yeah, more about my background in particular to this presentation. I did study geology at the University of California, Santa Barbara. I also stayed there for about a year doing some lab research. I had field projects taking me to places all throughout California, Nevada, Iceland, Chile. And I also spent some time in the lab working on things like geochemistry, geochronology, and petrology, which some of those terms might go over people's head, but it's basically the ages of rocks. What are those rocks composed of? What is their chemistry and kind of their story? What made those rocks to be how they are today? So all of these awesome adventures and places and getting to get more familiar with them has just been a really great privilege to me and an awesome experience. Although I haven't stayed in the profession of geology in the classic sense, I have kind of carried that knowledge with me into other things. So, as you can see here, I have always been perplexed by the mystery of what earth science is. I couldn't spend days on end, which I have already, just getting familiar with it, trying to understand it and make sense of it, just so I can better understand how my existence kind of fits into that. And now that curiosity has carried over into a career in recreation. I'm now mostly a tour guide on cycling and hiking trips. So I get to share that knowledge with people when we're on our bikes, riding through beautiful places, when we're hiking through awesome places. It helps kind of guide what routes I want to go on personally. I've got, my bucket list places I want to go. It makes road trips a little bit more worthwhile. Anyone who's been in the car with me gets a little apprehensive because I'm always like looking over and they think I'm looking at them, but really I'm just like trying to get a view and try to understand what's going on in the area. It informs some of the rest stops I might make. And it just helps me find purpose in the places that I'm in and where I'm recreating. So overall, geology has just given me a sense of purpose and belonging to this massive ball of rock. And I really find joy in helping others foster a similar relationship, rather than just being focused on the bike or, the hiking and how it's feeling carrying a big backpack or whatever. Thinking more about like the land that you're interacting with and what it really is important to me. And if you recreate outdoors, you're already one step closer to being a geologist just by being there. So hopefully this information that I'm giving you today will kind of take it a step further towards really being a geologist. But before I even get into the thick of this, I do want to acknowledge the importance of Indigenous land acknowledgement. I think when we're talking about nature and the land and trying to be respectful and be a steward of that land, we really need to acknowledge who were the original stewards of the land. So just a quote from Northwestern University, it is important to understand the long-standing history that has brought you to reside on the land and to seek to understand your place within that history. Land acknowledgements do not exist in a past tense or historical context because colonialism is a current, ongoing process, and we need to build our mindfulness of our present participation. I find it's just really important to acknowledge this because land acknowledgements are more than just saying, oh, I'm on Chumash land, which is known as Santa Barbara. Like it's much more than that. It's actually understanding the struggles that they are currently going through right now in the San Marcos foothills. Um, and this is just kind of a list of points to also consider more beyond just saying where you are. What is your intention on that land? Making sure that you actually learn from the community, learn how to actually say the names right, learn who still exists there, who is still a steward of the land there, understand the history of their people on that land, and how, like, the reality of what's actually happened. Don't sugarcoat it. People have been wiped out. There has been erasure. We need to be very clear about that. Also acknowledging their presence, that they weren't just there in the past, they are still existing. Celebrating their existence and empowering them by supporting them, asking how you can help them, and paying them for their time and their labor. Land acknowledgement is just a start. So I just want, while I have this space here, to emphasize that, the importance of that. And with that, let's move on to just talking about the purpose of this whole presentation, which I've kind of already gotten into, but I just want folks to kind of learn how to think like a geologist, how thinking like a geologist can help you plan and prepare your trips with this like newfound context for the land. It adds value to your time in nature because you have a better understanding of the nature that you're on, and just having a deeper connection that will allow you to take better care of it. It is Earth Day. Of course, Earth Day is every day. So hopefully this just gives you a deeper respect and connection to the land that will allow you to take better care of it. And we're going to just rock and roll right through this. All right. So to talk about geology, we're just going to go over some basics. Uh, when we talk about geology and the processes that are involved in geology, we have to talk about time. And geologic time is really hard to fathom. It's kind of the first thing you have to grasp as a geologist is how immense geologic time is, how long it takes for the Earth to go from this big molten blob 4.6 billion years ago to eventually becoming this beautiful, diverse, blue and green planet with teeming with complex species, that is able to inhabit people like us who are right now remotely watching a presentation about said thing from someone in a sun hat and a Hawaiian shirt. So the Earth has come a long way. And just to better help you kind of conceptualize what that amount of time really is, I like to, I'll have a good analogy for this, but usually you see really complicated, detailed geologic timescales like this. If you haven't seen this before, essentially it's a way for us to divide up and kind of make sense of all the events that have happened through Earth's history, starting from the Big Bang and that molten rock forming within our solar system, through the many mass extinctions, the formation of life, through the evolution of the human species. So many like events just parsed up over this time scale. It's very complicated and it's overwhelming, and there's no reason you have to understand it. What I can say is that a lot of what we know about the time scale has really only been formulated in the last few hundred years. So a lot of these names, have been made up by people who have studied these things. Maybe it's the names of the fossils that they found that they were able to get ages of that give them a timing of, okay, well, we know that, the T-Rex existed at this point. We know that this plant existed at this point, and that kind of dictates the name of the era or the Eocene or whatever it is. Those are a lot of details you could spend much more time like studying, but really I just want to make more sense of what this scale really is by looking at an analogy, something that we look at every day, which is a clock. So if we think of geologic time, 4.6 billion years, being scaled to an hour. There's a lot that happens within that hour. It's a jam-packed hour. And of course, you can see here on this diagram, there are a lot of events that are listed and taking place. But there's really just a few that I want to highlight. If the Earth is forming at 0 seconds and 0 minutes, it still takes over a whole 9 minutes for the first signs of life to appear. And this is in the form of single-celled organisms like microbes, which eventually evolve over 50 minutes of this hour. That's a majority of this hour that it takes to eventually evolve into the human species, which has only existed for 0.1 seconds out of that whole hour. So we've gone from little microbes to folks riding on 2 wheels, shredding on trail it's taken 50 whole minutes out of that hour, which is 5.6 billion years, which really it's like 3.5 billion years of evolution of life, which is immense. So that just gives you a better sense of like, if you're to think of the whole Earth's history within an hour, it's taken a really long time for us to get to this point. And so many events have happened in between. So really, it just gives me personally an appreciation for when I'm out on the land and I see different features and different geologic formations like the Grand Canyon or, like massive mountain peaks like the Tetons. I realize that these processes have taken a really, really immensely long time. And it makes me feel a little insignificant. But I mean, the fact that within the 0.1 seconds we were here, we're almost able to make the Earth uninhabitable for ourselves is really astonishing, the influence humans have. But beyond that, now that we have a little better of an understanding of time, we can think about the processes themselves. So the Earth started off as this molten rock 4.6 billion years ago. And now, today, it exists as this diagram shows. It's got a really super hot inner core, and it's surrounded by more layers of warm, molten, mushy rock. And then we have this really thin layer of crust on the outside. And this is due to the Earth just cooling very slowly over time. When the Earth was first formed and was molten, it was like a homogeneous mixture of just iron and nickel and different metal elements that are just all kind of blobbed together. But as it's cooled over time, it's differentiated. Different chemical processes have taken place that allow different elements to form and to separate because of the force of gravity also affecting different elements differently. You can I like to think of it as like a cup of tea. If you have a cup of really hot tea and you pour sugar in there and you mix it around, the sugar dissolves and it becomes a homogeneous mixture. That basically means it's like everything is the same. But if your tea was really cold and you tried to mix sugar in there, it would hardly mix at all. And actually, if you let the tea sit long enough with dissolved sugar in it, that sugar eventually will start to crystallize as the tea becomes cold. So it starts to separate out again. And that's just kind of an analogy for what's chemically happening inside the Earth over these billions of years, is that as it's cooling, different elements are forming and things are starting to differentiate. And that's kind of how we get all of these layers. I also like to think of the Earth as a big gooey cookie. It's like, when you first take that chocolate chip cookie out of the oven and it's nice and gooey, it's all cohesive. But then as it cools, you notice the surface of it start to crack and separate. And if you pull it off the pan, though, and you pull it apart, that gooey inside is still there. But also, if you left the cookie too long and you went to go get your cup of milk or whatever, and you come back, and then you notice that it's not gooey anymore, it's almost completely solid, you waited too long and the cookie totally cooled. So essentially the Earth is like a giant chocolate chip cookie that's just cooling over a really long period of time. That's a bit of fun for you. But back to the nitty-gritty, the Earth is made of layers, and these layers and the differentiation of them and the cooling that is happening all across them is causing all kinds of processes to take place. You know, just like the cracking of the cookie and heat escaping through those cracks, the Earth has to do the same thing in order to accommodate the heat that is attempting to escape as the Earth cools. The crust is essentially cracking by having, you know, all these puzzle pieces of the continents and the masses of water kind of shifting and working together to be able to circulate that heat out of the planet, and allow it to continue to cool. So if we're going to talk about, you know, these processes, at a small scale, we first need to talk at a big scale about plate tectonics. And plate tectonics have really only come into the picture of geology and understanding in the last century. Before that, you know, there were all kinds of crazy ideas about, you know, why volcanoes existed or why magma existed, or why mountains existed. But now we have a better understanding of why plate tectonics is actually a better concept to make sense of what's going on the Earth. Essentially, it's like I said, it's puzzle pieces. So all these different plates all over the Earth are basically shifting and moving. Some of them are spreading apart. Some of them are colliding. Some of them are subducting under one another. And all these different tectonic regimes where these different processes are happening, it's creating different types of terrain, different types of rocks, and it's affecting the Earth's crust differently. So when you're out, you know, in nature and you're in different places and you wonder why you're riding along, and, you know, maybe when you're riding through Utah, you see all these massive deep canyons, but then you go over just a couple 100 miles and you're in Colorado and there's these towering mountains. Then you go over another 1,000 miles or so to the East Coast and you just see more forested areas. You see more mangy looking gray rocks and mud, and just, you know, it's perplexing to wonder how can the Earth be so dynamic over these spaces. But it's really because you have so many different processes going on to make, you know, to accommodate what's happening at the core all the way out to the crust. So over time, these plates have shifted. They have taken on different orientations and moved all around the globe. So the Earth is really dynamic. It's not really this stagnant, solid thing, you know. It's really just, it's constantly changing. And although we don't really get to see those changes taking place that much in real time, it's happening over these millions and billions of years, and it's going to continue to happen. So understanding that there are all these different types of processes going on helps us to better understand maybe why rocks are so different. And I'm going to talk a little bit about kind of generally what the cycle of a rock's life looks like. This is very generalized. You can get really nuanced into smaller cycles that are happening just within each of these stages. But for the most part, this is kind of generally what's going to happen. You know, rock first starts as molten. It's melted. And what happens is, what happens is when that rock comes to the surface of the Earth through volcanism, through volcanoes, through the spreading center between two plates, due to subduction and the melting of a plate under another, or just due to random hotspots like Hawaii, when that molten rock comes up through the surface of the Earth, kind of like a popping pimple, it cools rapidly and it forms new rock on the surface. So the Earth cooling in general has formed a rocky, you know, crusty surface, but we get new rock every time this magma makes it out to the surface from the mantle and the core all the way over onto the crust. So now you've got this hard rock, new rock, and essentially that rock is going to experience weathering and erosion. This is in the form of wind carrying it downslope or water carrying it downslope. Notice I keep saying downslope. That's because gravity is also a huge factor. Rocks can't just like fly off into the air. They're always going to go down with gravity. So as they're eroded away from their source, they essentially become what we call alluvium or sediment. So when you're in a valley or you're in a canyon below a mountain, that's why you see like these huge piles of rock. And sometimes it looks exactly like the mountain you're next to, but really it's just the chunks that have just kind of been wearing away. And then once you have all this sediment and rock collected, it will start over long periods of time to experience compacting and cementing. And that's why sedimentary rock usually has some kind of layering, because all sedimentary rock is just it's like a mishmash of rock that has formed from events of erosion. So when you think about rocks like sandstone or conglomerate or limestone, maybe these names sound familiar, maybe they don't. They'll get a little more familiar as we go along. But these kinds of rocks are sedimentary rocks simply because they're a combination of rocks from other places, which were probably initially igneous rock, and they've been carried into this place through erosion, and they've been deposited, and over time, pressure and water has lithified, which basically means like cementing the rock into becoming a whole new rock now. And of course, that's going to change the texture of what that rock originally was. Another thing that can happen is, it doesn't necessarily have to get buried in a lake or a river like this illustration is showing. A rock can also just be buried in sediment itself, in a valley or on a hill slope where sediment is constantly coming down. When rock gets buried deep enough and closer to the mantle, it gets a lot warmer. It's reaching greater depths within the crust and the earth where the temperature is increasing and the pressures are increasing. And whenever a rock is experiencing high temperatures and pressures in contact to hotter molten magma or the mantle, it's going to metamorphose. That means the chemistry is going to change, the texture is going to change. That's more of those chemical processes that I was kind of talking about originally with the earth cooling, but it's just happening at a smaller scale with rock. So rock that originally was igneous, maybe, it became a sedimentary rock by getting piled into layers and layers within a valley, eventually will look completely different from all of these processes of metamorphism. And then eventually, if it gets buried deep enough and it cycles through and it ends up at a part of a plate in the crust that's going to experience melting, well, then it just turns into magma again and it becomes a part of the mantle again. The earth is what it is. It's a closed system. So everything has to be cyclical. Everything goes through a cycle and things are changing as that's happening. So now that we've kind of talked about processes from a big scale and a smaller scale, let's talk more about how this dictates different types of rock, what these different types of rock look like at a small scale, and also what they look like out in the wild. So first we'll talk about igneous rock, which essentially means rock that is primitive magma that has been cooled. And igneous rock isn't just one type. It's not just granite. It's not just basalt. It can look very different, and that chemistry can change based on how that rock was melted, where it came from. Did it come through a really thin section of crust where the crust is stretching? Did it come through a hot spot like Hawaii? Did it come through a subduction zone where it's going through a very thick amount of crust like it does in Alaska or on the California coast? Depending on what all those conditions are, it'll change the chemistry of those rocks. So in geology, just to give you kind of a snippet of how we can really get bogged down in the details, most folks think of granite, like people refer to a lot of things as granite. Oh, it's granite. Oh, it looks like granite. Granite countertops, granite mountain. And not everything is granite. Granite is actually a very specific term, which you can see on this diagram on the right. It's really just based off of percentages of what kinds of minerals are in that rock. So if you have just a little bit more plagioclase feldspar or a little less biotite, now it's a diorite all of a sudden. But it could still look to most people like what classic granite is. If you want to get caught up in all those details, you're more than welcome to. There are plenty of books and diagrams offering this sort of information. But for the most part, I just want to show that, with igneous rocks, there's all different kinds and types. Not every volcano is the same. Not every rock is the same as a result. And so they're going to have different textures and different colors and just different appearances overall. And we can see this in real life when we see features like the Torres del Paine, this beautiful, just like pinnacle-like ridgeline of rock. We also see like places like Yosemite. This is Half Dome pictured here, which is also intrusive igneous rock. And then we have places like Joshua Tree, which, it looks like it's just a bunch of boulder piles. But it's essentially the same stuff. It's also igneous rock. The only difference is the composition is slightly different and the conditions they've experienced are different. You have desert terrain in Joshua Tree versus more alpine terrain in Yosemite. So they're experiencing different types of erosion as well. That's kind of changing how they look. And fun fact, these boulder piles in Joshua Tree are actually known as Inselbergs. And they're not piles of boulders. It's actually cohesive rock that has just experienced patterns of fractures and water intruding those patterned fractures to kind of round them out. And you can kind of see here in this image, like the patterns of the horizontal lines, the vertical lines, some diagonal lines. And that's a whole other spiel I can go into. But basically, there are different conditions there that are affecting that rock differently and making it look differently. And then we have volcanoes. If some of you don't recognize this volcano, it's a volcano that's currently erupting in Iceland. I'm pretty sure it's still erupting. But it's actually not even just one volcano. It's actually a whole line of vents that are releasing magma right now. But this is also igneous rock. This dark black rock that forms after this magma's cooled is also igneous rock. But it looks totally different, right? And it's also in Iceland, so it's going to experience different conditions like ice and really harsh winters and wind that are going to erode that rock much differently and make it appear different. The next rock type we're going to talk about is sedimentary. So kind of as I was mentioning before, sedimentary rock is really just like the secondary version of igneous rocks. Igneous rocks basically just broken down and put back together in a different way. But it also could be fossilized rocks. I like to think of sedimentary rocks as life rocks because they show evidence of life by the movement and the reorganization of the igneous rocks, but also it's evidence of life in these lake beds. The deposition of calcium carbonate, which is essentially just like shells and dead sea life accumulating on the sea floor. It could also just be, fossils in another sense, fossils of other forms of life. So like petrified trees, fossilized bones from dinosaurs, and all kinds of life and plants and such. And it's also the result of microbes that still exist today, of course, that will like secrete certain elements that still form layers. So things like stromatolites. But basically, to me, sedimentary rocks are like the rocks of life. They show evidence that there is processes going on Earth, and that there is life, and that there are things that are, living. And of course, as you can see here, they could look very different. They can be very colorful. They could have, a lot of them might have layers, or they might just look like a mishmash of rock. So they can look all very different, but they are all sedimentary rocks, and they express themselves differently in larger rock features as well. But when we're classifying sedimentary rocks, and this is just another little like window into the details, we really classify them by kind of what was the type of erosion or weathering that formed that sedimentary rock. Was it due to being in close proximity to a mountain where the clasts are going to be really big and angular, and they're all just kind of mishmashed? Or is it going to be farther away from the source where things are a little bit smaller and rounder, and you might actually have some episodes of water having risen there and accumulating salts and things, evaporites is what we call them? Or was it mostly within the ocean or within a body of water where things were deposited? And you can also see evidence of calcium carbonate being deposited by the life that was existing in that water. And we look at things like class size in order to determine that. We look at what kind of chemicals or elements are in that rock. Are there biologic elements that would, when we think of coal and we think of fossil fuel, we think of like dinosaur bones and things. But it's not all that. It's literally anything that was living, anything that was composed of carbon, could form biochemical rock. But these are just some of the classifications we can use, and that just gives us a better sense of where that rock came from and how it formed. And we see this in the field, we call it, or outside, like this large feature, which might be close to a deep like river canyon where there's a lot of activity, and kind of like aggressive erosion. You can see the clasts are really huge. We would call this a conglomerate. Or somewhere like Badlands, you can see the layers of what's probably mostly sandstone, maybe some small layers of limestone, depending on whether, during those times, there might have been periods of time where bodies of water were over this mass, and limestone accumulated. Or places like, Moab, we have the arches here, and that's mostly going to be composed of sandstone, but the feature's slightly different, and it's very unique because there were salts involved, and that's a whole another talk I could do. But at depth, there were other things, blobs of things within these layers that affected how they eroded as well. We have layers of limestone here forming mountains, which at a glance, might look like, oh, it's like a granite mountain, it's gray and it's big and rocky. But when you look at it, it actually has all these really pronounced layers in it. And, granite isn't going to form layers like that because it's not sedimentary. It's more bulbous and blobby. So you might see differences in how it looks over large scale, but you're not going to see really well-defined layers like this. So it has to be sedimentary. And then, yeah, just a beautiful, pristine dune here. That also is going to form sedimentary rock. And although it looks like it's one homogeneous mound of just like sand, there are some layers going on there because as the wind is blowing up against these dunes, there are elements that weigh different amounts, like magnetite is going to be a little bit heavier than quartz. So you're going to see it kind of accumulate in ways that will actually show layering over time as it's lithified. And you'll see fossils. You can't see fossils in igneous rock. It would just get melted. It's not possible. So it's got to be sedimentary if there's a fossil involved. That's just like a given. Now we're going to talk about my favorite rocks, which are metamorphic rocks. And the reason I love metamorphic rocks is because they're like a murder mystery. It's like you had a rock, you had an igneous rock or a sedimentary rock at one point, and it has since been cooked, pressurized, and moved around. And so it has a whole new appearance. And it's just fun to think about maybe what it once was, especially because as you can see in these examples here, you can still see layering, in these rocks, but they're mangled and folded. And there's these huge crystals now that almost look like they're pushing up against everything else. And that's because the chemistry has changed from what it originally was. But there's kind of a system for understanding, based on chemical and physical processes, what those rocks must have once been in order to become what they are now. And our classifications for those are mostly dependent on pressure and temperature, which can also mean how deep were they. Was this rock that was buried deep enough and close enough to a body of warm molten rock, like a magma chamber, that there was a lot of change in the chemistry, and that it almost experienced melting and a lot of folding? Or is it just kind of like slate or shale, where it's just experienced a lot of pressure, maybe not a lot of high temperature, but it's just experienced enough pressure that instead of just being like layered mud, it's now solidified and it's hard and it's slatey. It's got a texture to it. So that's kind of really just how we classify what different types of metamorphic rocks are. You can get deeper into that if you'd like. But metamorphic rocks are deceiving, man. They can look really similar to what they originally were, when you're looking at them from a distance. But if you ever get a chance to go up close and kind of test your eyes and see, is it really what I think it is? It could just be a fun game. Like this mountain here looks like, oh, it could just be another granite mountain. But no, if you really look at it, you can see that there's a texture here. There's folding. And in order for something like granite to even get some kind of texture like that, it would have to experience really intense pressure and temperature that would cause that kind of deformation. It's also caused by things like faults, which I didn't want to get too deep into structural geology in this talk. But essentially, with plate tectonics and all those plates moving around, at a big scale, it's almost like they're giant faults all between each plate. But also at a smaller scale, there are, faults that are also accommodating that, and there's movement along them, and it causes the folding and crumpling of rock as well. But anyway, when that's happening, rocks are metamorphosing because they're experiencing pressure and temperature of getting all mangled. Like this rock here, which is also called a hornfels. This probably was definitely a sedimentary rock at one point. You can see the layering in it. But the composition of that rock is much different now. The hardness and texture of that rock is much different now, and that's because it has experienced higher pressures, possibly higher temperatures that have caused it to change. This is obvious. You can see that the layers here things don't get deposited like this usually. They're usually going to be deposited, very planar. So if you see something like this, you can assume that it's been metamorphosed. It's folded and mangled, and you can even see the fractures and cracks all within it. And then this is also something that at a glance might not seem metamorphic. It might just seem like, oh, it's just like, a pile of rock or whatever. But really, if you look closely, you can see kind of layering to it and patterns. And if you look at the individual pieces next to it, you can see they're like these slabby, platey rocks. And, sedimentary rock can somewhat do that. But if it's to this degree where it's very hard and it's like, kind of bended and folded a little bit, it has been metamorphosed. When you're out there, this isn't like really a huge distinction to make in terms of like how your bike's going to ride or something like that. But it's just fun to know, oh, okay, like that little rock has experienced some things. It's been through some things. It's been through some cooking and some tough times, and it's still here. um, so those are the different types of rock that you would see out there. Now let's get into what you probably really actually care about, which is how does this affect the conditions of the trails that you're on? Like I've said before, different rocks have different textures. Different types of erosion create those different textures. Whether you have a mountain or something that looks like a boulder pile, that's going to be dictated by kind of the conditions that those rocks are in. And then even just the way that a road or a trail is built is going to influence the texture. How much time and work has actually gone into, establishing a trail, and the manner at which it's been established can also dictate that. So although we can kind of learn about an area and learn what kind of rocks are there and predict what the trail might be like, there's also human involvement. There's a human influence that will also kind of change that as well. So that's just something to account for. Trails could look rocky and steep like this, real chunky. They could look ruddy and kind of hard packed. They could be lovely, kind of stepstone. Obviously, there's a lot of human involvement in something like that. They could be just nice, kind of a little bit more like single track, kind of hard packed rock trails through the trees. It could look like switchbacks going down into a deep canyon, or it could look like some nice flowy sandy single track in the middle of the desert. So, all of these different scenes have different types of rock, different types of erosion that are influencing the trail. And of course, you can see that, some of these trails have probably gotten a little more work than others in terms of like human maintenance. So, kind of talking about a couple cases here, the main things to think about are how much exposure is going to be in that area and what type of rock is in that area. Those are kind of going to be the two biggest influences to consider if you're going to consider any at all. So we're just going to think about three different cases here. First case being an area with really high exposure and hard rocks. That basically means there's not a lot of vegetation, so it's really exposed, and the rocks are hard, meaning they're rocks like granite or limestone or metamorphic rocks that have a really hard texture to them, maybe very crystalline. The kind of elements that are in them aren't easy to break down, so the nature of the terrain itself is just going to be chunky, and it takes a lot more work to break down. And so that's why those trails will tend to be a little bit chunkier. You might notice, when you're in a high exposed alpine area that, you're gonna go over some boulders. You might have to hike a bike. And that could also just be because they're a little more remote and less maintained, and it's just more expensive to break down really hard, tough rock like that. But the exposure detail, the exposure factor, is really just because there isn't going to be a lot of soil. If there's no vegetation, there's not really going to be soil, that life is producing or supporting on top of these rocks. So it's really just the rock itself. The next case is a case of you still have really high exposure, not really any vegetation, but the rock is soft. And when the rock is soft and you've got a lot of exposure, you're going to tend to have softer trails or hard packed trails. That basically means, if you're in an area where there's going to be, like here on the left, you can see there's like sand dunes. This is like in the middle of a desert valley where all you're really going to have is sand that has accumulated from all the mountains far off in the distance surrounding. And it's going to be really soft because there isn't a ton of vegetation. There's a little bit of vegetation, But for the most part, there's nothing really rooting that sand and soil together to make it hard. It's just going to remain soft with the little tiny grains of sand. And on the right, it's a little bit more hard packed, but it's probably just because of weather, when there have been recent rains that can help to lithify, remember lithification and cementation? That sand and rock and pack it down a little bit more. And even if the grains get slightly bigger, they're not quite sand, but maybe it's more like gravel. But the wind that is frequently going through is kind of carrying away a lot of that dust and making it a little bit more hard packed. The last case is going to be a case of low exposure, meaning high vegetation. You're in the middle of a forest, maybe in alpine areas, or even in low elevation areas that just have a lot of trees. I know Swift Industries folks are probably very familiar with this kind of terrain in the Pacific Northwest. And they could probably speak to this too, but those trails are going to be combination trails, is what I like to call them. You do have the factor of soil because you've got a lot of vegetation. So you do have sections that might have enough soil to kind of give you some cushion, especially if it's well maintained and people don't beat up the trail when it's wet. Then, you have some likelihood of having these like soft, flowy trails. But there's also a possibility that you'll have some rocky trails, sometimes in really steep terrain where soil doesn't really stick as much, or you still have a lot of frequent downfall of rocks. You're going to still have some rocky, chunky trail. I mean, also, yeah, they just mentioned the roots. Oof, yeah, you're going to have those exposed roots to kind of deal with too if the soil isn't high enough above that vegetation. So those are just like some of the most common cases. Of course, those things can change based on the terrain. But that's just what I like to think of when I'm planning on going out into an area is how exposed is it going to be? What type of rocks do I know are there? And that gives me a better sense of kind of what to expect in terms of should I take my mountain bike because I will need suspension? Or could my gravel bike probably handle it because I think it's mostly just going to be hard pack in the middle of the desert and it's not going to be too crazy. So it just kind of helps inform those decisions a little bit. And it also just helps you make sense of when you are on a trail, why these textures are occurring. And these are a lot of different cases. How do you even decide from here? Okay, well, so what kind of trail do I want to go on? Now that I understand a little more about geology and how the rocks are kind of affecting the conditions of the trail. What does this even mean for me choosing a route? Well, I can tell you that the biggest way to kind of help make that decision of, well, now where the hell do I want to go knowing all this? It's really just maps. I love me a map. As you can see, I love me a good map. And really, maps are what's going to help kind of inform those decisions. Just having all this knowledge about rock types and processes isn't going to do much if you don't have a visual for the area that you're trying to go to. So let's talk about different types of maps, reading maps, and how this can help inform your decision. So we're mainly just going to be talking about geology maps, since we're talking about geology. And they can look very colorful and beautiful and also very complicated. But the biggest takeaways is that what they're showing you are the rock types. They're showing you the rock types. They're showing you how old those different layers of rock are. They're showing you what rock type is actually at the surface. So all these really cool shapes like the orange, the green, the purple, those are the rocks that you're going to see at the surface. Once you go beneath the surface, that could change, because rocks are at 8 different angles and orientations because of all the mangling they've experienced with plate tectonics. But you can still understand what they're like on the surface, and that'll help you inform kind of what the land is going to be like when you're there. It also tells you scale. It's going to tell you, you can see these little bars right here, 0 to 40 miles. So that, that tells me that this little section is probably about 80 miles wide of late tertiary valley fill, which that, to me, that means, it's most likely going to be sedimentary rock, valley fill, sedimentary rock. Or if we want to, see these volcanic rocks, well, these high mountains here in southern Utah are mostly composed of these volcanic rocks. So if that's what I want to see, that's where I'm going to go because I know it's on the surface. Sometimes the geologic maps will also show you all these lines. You see these black lines all throughout. Those are just representing things like faults, things like folding, and veins. Cool. Veins are just mineralizations of other types of rock in cracks and fractures of the rock. Again, another spiel I could go on to, but it's showing you basically the rock types at the surface, where they are. It's showing you the scale, so kind of how big that area is. And it's also showing you what the structural makeup is. What are the faults doing? And then sometimes you'll see things like this little square on the right, and that's a cross section. Where is that line at? That's a cross section that's actually showing you at depth what is going on with the layers. So this is a lateral cut. It's literally like if you were to slice across here and cut down into it and look at it head on, this is what the layers would look like. And that's not necessarily super helpful for, understanding the surface, but it's still cool and informative to know, oh, okay, this is what's going on, like underneath all these layers. Now, if we're just to look at a small subsection, these geologic maps can get even more detailed. So if we look just even at the Moab area, we can see that it's even more complicated. You can't see all these little colors and lines within that square. It's generalized when it's at a bigger scale because you're not able to see those details from a bigger scale. But when you're going into an area, you can likely find smaller scale maps just for that area that you're concerned with, and you can see even more fine-tuned details. So depending on the amount of ground you're going to cover, that will kind of dictate what size of a map you should really be looking at to inform the land that you're going to be on. And this is super complicated, but it's more of just showing the structural stuff that's going on with all the different rocks there. And of course, this is still showing different rock types. So geology maps are great to get a sense of what the surface of is actually going to look like, what the texture is going to be like. But then you can also look at topographic maps. And people are usually looking at these before they look at geologic maps. But these aren't going to tell you anything about the type of rock you're experiencing. It's just going to tell you about what the terrain is like, whether it's steep, whether it's gradual, whether you're in the mountains or in a valley. This first map here is kind of just a colorized gradient topographic map, which means each color represents a different section of how high the elevation is within that blob. So like the darker the green is here, that means the higher the elevation is. And this is also Utah, so you could see the Salt Lake, and similar to the last screen, you could see these are all the mountains here, the volcanics, and they're going to be at a much higher elevation, probably much steeper. Another illustration of this is 3D relief maps, which are super cool. Google Maps offers this. Most of the apps like Ride with GPS and Komoot and Strava offer this like 3D relief layer where you can actually see kind of in 3D what the elevation looks like. You can see the high mountains, you can see the canyons. And then kind of the classic topographic map, what you're usually going to see when you buy a topographic map at a store or online to print, it's going to look like this, which is like, what the hell is even going on? If there's a lot of lines here, it's very busy with just lines. But this is a pretty big area. Normally maps like this are going to print out like huge. or they might print out in sections for an area that big. But we can make sense of this if we're able to kind of visualize it within our minds and then kind of get an idea of the perspective we're looking at here. So to make sense of that, the way a topographic map is even made is essentially taking the topography and drawing contour lines of the same elevation around that topography, all around it. So in this 3D model, you can see that 1100, which there's no unit here, but I'm assuming it's like 1100 feet. This line represents that. So wherever that line touches, that is going to be 1100 feet. And wherever you drop on that, like wherever you are in 3D space on this mountain, this will help you understand where you are elevation wise. So if you were here, you're between 1200 to 1300 feet. If you're here, you're at 1400 feet. And then this is what it looks like on the map. It's basically just a smushed 2D aerial version of what this would look like if you were looking at it from above. So from above, features like, a tall, steep mountain and a gradual mountain would look like this. The lines are closer together here on the steep side, farther here, so it's a little more gradual slope. A very gradual kind of pointy mountain like this will kind of have this look. You can tell it's a ridge line because, this axis is a little bit longer. It's a little bit shorter on the sides, so it's more like a thin shape. And then something like this, like a canyon, you can see that there are two pronounced domes right here. And these little circles are the very top. And then this is the canyon in between. But that can also be deceiving at times. But follow the lines. Each line is the same elevation all around. And how close or how far those lines are tells you how steep or how shallow that slope is. So if we're looking here, this is a topographic map of the North Kaibab Trail in the Grand Canyon area. And you can see where these lines are like really, really close together. They almost look like it's a darker shade, but really the lines are just so close because they are sheer cliffs. That elevation is changing rapidly. And then places like over here where you see the lines really spaced out, that's more of a mesa. That's going to be an area where it's more just flat and extending out, but then you can see there's these darker shades where it's dropping. And we can see evidence of that by the fact that there's a river here. Rivers form in canyons, not on the tops of mesas. So naturally it makes sense that, there's darker, more close together lines here. And this is what it would look like. You have these kind of like mesa-like features here that are a little bit flatter on top, and then they drop with these sheer cliffs on the side. You can see the even deeper canyons down here, which is similar to what we're seeing from the aerial point of view here. So topographic maps just help get a sense of what the topography actually looks like. Geologic maps help you see what type of rock you're dealing with, but topography maps are going to show you kind of what the 3D structure is actually going to look like as well. So by understanding both types of maps, you can now make some map magic. By combining the power of the geologic map and the topography map, we can make better sense of the land that we travel on beneath our wheels. And we can see into a future of beautiful bike riding or hiking or whatever kind of recreating that you're doing. It really can be magical if you think of it that way. But with that, all of this, with being able to understand rock types, being able to read these different kinds of maps, while you're out there, once you've actually planned the whole ride or the hike or whatever it is, and you're finally out there, you can, by knowing ahead of time all these things, you can better identify, what kind of rocks am I actually seeing out here? Take a moment, stop and pause. Look at what the rocks are actually doing, what the textures are like. Make sense of it. There are little pocket guidebooks you can take that will help you make sense of that. It'll help you predict the road ahead. If you know that you're starting low in the valley where maybe there's not a lot of exposure and there's a lot of trees and the trails are a little bit softer or chunkier due to roots, but you know that you're about to try to summit up to a peak where there's really high exposure, you know that that trail eventually is probably going to get really chunky, way less maintained, a little bit difficult to cross. So you can just kind of better predict what's going to happen just by knowing your surroundings. And it also just helps with survival tactics. I mean, just understanding the sense of gravity, that what goes up must come down, knowing that, water sources are going to be more likely found in a valley or a canyon than they are up at the top of a peak. Although there are springs, but that's a whole other thing to get into. But also just understanding the differences of exposure, understanding how different rock types form different types of formations and structures that might allow you shelter. Um, there are all kinds of things to consider just by having a different newfound context of, you know, uh, geology. You can get a better sense of kind of how you can adapt to the area that you're in and survive off of it. So now I just want to get into talking about what resources are available for this kind of stuff. Like, where do you even find maps? And there are going to be more resources than what I'm presenting here. This is mostly just stuff that I use. So you're welcome to go beyond that. You're also welcome to suggest in the chat what you personally use. I'd love to see what everyone else is using. I love USGS. They have an awesome interactive map viewer online where you can see the maps that have been kind of widely accepted and published all over. So not just national, not just the US, they also have maps available all over the world. And, these maps are done by humans. So they aren't all very accurate. Some of it's done by satellites nowadays, actually. Of course, we have to do that to research places like Mars. But so they aren't all super accurate. They might not be as precise, and you might not see all the fine details you would want to see in a really small area. But you can get a general sense, at least, for most areas. USGS is awesome for an online resource. And if you want to just find like publications and prints in tangible forms, I know some of y'all have probably seen these displays before when you go touring somewhere at a national park or at an outdoor gear retailer. Those little things are actually great. Sometimes they offer some great free maps, or maybe they're for sale. But sometimes those things have good offerings. Also, National Geographic has a ton of maps for all kinds of places. Of course, this little Rolodex you're seeing here is for the Pacific Crest Trail. That just goes to show you that they have a lot of really detailed maps for a lot of quadrangles, which is really awesome. Usually, like, park visitor centers will have more things like geologic maps and such. But also, like, your local resources are the best resources. Going to your local library or university where they're actually doing the research for that area is going to be the most reliable. They're probably going to have the most up-to-date information for maps. Your local geology department. You can also look up scientific journals if you're going to a new area that you're not going to be able to interact with the locals for, and you can see publications for information on the geology or the topography of that area as well. Beyond maps, there are also books. If you're just generally interested in geology now, and I've got, that little itch going for you, there's some interest. There are a lot of books, but some of the books I've enjoyed are a couple of these books by Marsha Bjornerud. Timefulness is a personal favorite for me. It's kind of just thinking about life and everything in terms of how a geologist thinks of it. thinking about time from a geologic standpoint instead of a human standpoint, which can be very selfish and minute and minuscule, is really helpful. And the Smithsonian Earth Guide, for someone who needs to look at things in terms of visuals, this book is perfect. It's really almost like a collection of the podiums that you would see at the museum. It's almost just like page after page after page of that, just like beautiful illustrations and visuals and small explanations of things that are really awesome. Great coffee table book. And there's also the series of Essentials of Geology, which it's an introductory book that most geologists have to read in college. Of course, the most recent version is probably super expensive, but you can find older versions that are just as good and much cheaper, and will have literally everything, all the basics of geology, more in depth than what I've gone over today. There are also really cool guides you can take with you out in the field. National Audubon Society, and of course another Smithsonian book. And these books are mostly just for identifying rocks and minerals. They'll tell you more in-depth things like the chemistry, kind of where they come from, how to identify them. But I think it's cool just to kind of have as like a little like checklist, bucket list of like, okay, like I found this rock today, or I saw a neptunite today, I saw a labradorite. It's just kind of a cool little compendium. The last thing are just guides. One of my favorite guides that I take with me when I am guiding is this Pocket Naturalist Guide. I actually have it with me here. And it's really cool. You can see it's really small. I can fit it in my backpack or in my pocket if I really need to. But it has really cool information and great illustrations of different types of rocks. It has these generalized maps of kind of what kinds of rocks you're going to see in different parts of the US, which is very generalized. But it's really cool. And it's just a way to kind of whip it out really fast and like spit some knowledge, or just double check, like, is this the rock I'm seeing? It's available at most national park stores. There are also these guys. So many guides. These are the roadside geology books. Unfortunately, I only know of them existing in the US. I don't know if they have a similar thing in other countries. But they have them for most of the states. I think they have them for about 30 something or so of the 50 states. And they are so awesome. I totally encourage you to have one of these for whatever state you live in, because it informs any road trip you go on. Most of the major roads are involved in this, but there are pictures, there are illustrations. I have the roadside guide of Southern California here, and yeah, there's like geologic maps. There's really cool pictures of the places, and it also has an introduction, kind of similar to what I went through today, of like what geologic processes are kind of taking hold of the area that you're in, or like what the history is like just within your particular area. So really anyone, even if you're not like a well-versed geologist, or even if you don't feel like most of this went over your head today, these books are awesome for anyone to pick up and just get a better sense of the geology around them or in a new place. My goal is to collect one for each state that I go to, and slowly accumulate them over time, and just so that I can always whip one out whenever I'm in that area. They're great. The main takeaways here, is that I really want you all to find more value in nature, not just in the sense of like, the plants and the animals. Those things are great. I'm not trying to downplay those at all. I got a soft spot for rocks, but hopefully learning more about the surface of the earth itself and the processes that have taken so much time and energy to create these beautiful places that you get to adventure on. I just hope that all gives you a better, deeper sense of appreciation for these places that you have the privilege to see and witness. And with that, I want everyone to explore with intention, recognize that these places are very special, and that the people who have been taking care of these places all this time, before colonialism, really, deserve respect and honor and love and support to be able to continue doing that. And we should do the same. And just recreating responsibly in that sense, I think I saw someone's question about, rock collecting. I've been conflicted by that. When I first started my geology degree, I was like, oh, I'm going to pick up every single rock because this rock is cool, this rock is cool, this rock is cool. And over time, I realized, well, first of all, I don't have enough space for rocks. And second of all, rocks are cool, but what justice does it do to just like hoard them, it also doesn't do a whole lot of wrong to take them, but in some places it isn't right. Or trying to figure out the best way to describe this, but leave, for the most part, you should probably just leave places as they are. Um, Definitely don't hammer into a rock to remove a chunk of it and leave if, it's not necessarily going to serve you besides this chunk of rock just sitting in your house. To each his own, but I just have to say I've gone through my own process with that, and I've just realized that there isn't any real purpose for me to hold on to them, and I'd rather just continue to get outside and see those rocks in the places that they are and just experience them, check them out, and then, go home. But that's just me. Definitely look into the areas you're going into. There are restrictions in certain areas about rock collecting, um, fossil collecting as well. So I would just say to, do the research, inform yourself, and know what you are and aren't able to do. Um, and just encourage that accountability in others, share all these fun facts with other people, get them stoked, get them excited, and help inform them on these cool areas they get to be in. If you're leading a trip or you're riding along with someone and you just need to take a breath, say, hey, I want to stop and look at this rock. Hey, actually I learned this thing. Just share that knowledge, but also just encourage other people to hold themselves accountable and how they treat the land and how they interact with it. And, I promise you, it's just going to make the experience even better. And that's all, folks. Um, I have really enjoyed giving you this presentation. I could talk at nauseum about geology, but I won't. But you're always welcome to reach out to me on social media. I'm happy to keep talking about this stuff, keep answering your questions, and I'll hopefully answer some of your questions now. And yeah, get out there and rock and roll, y'all. Let me know what you find out there.
Unmute. That was awesome. Thank you so much, Alexa. Can you hear me?
I can hear you.
That's great. Yeah, I had a question. If
Okay.
you could explain the phenomenon that is like Goblins Valley in Utah. For those of you that don't know that place, it's like this crazy sedimentary rock formation of these basically a bunch of little people like on pedestals. They're not people, but
that looks very like magical, fantastical.
yeah.
Yeah. So I haven't been there, but I assume it's the same kind of thing that's going on with, they call them Mexican hats. That's another term, which isn't necessarily super appropriate. But they look like big sombreros sitting on a pillar. And It's like, how the hell did that big, huge rock, pancake rock, make it on top of this like skinny pillar of rock? But that's mostly due to layers having a different composition and erosion eroding those layers differently. So the layers that are still really bulbous and are like kind of like the top hats or like the heads on top of the pillar, those are layers that were a little bit tougher. So they probably have larger, like stronger minerals and clasts in them that are harder to erode. but the stuff underneath was much softer. So over time, the softer parts have eroded like really much easier, forming these tiny pillars, but then you still have this bigger piece that's just taking a much longer time to erode. So it's still sitting there pretty intact. And they're connected still, but yeah, it's just different levels of erosion taking place.
Cool.
Yeah.
That's amazing. I know that one person had asked about finding the maps that you like before you talked about the maps, but could you just reiterate like the resources that you have for finding these geologic map layers for folks?
Yeah. So I mostly use USGS, which is the United States Geological Society or Geographical Society. It's either geological or geographical. Can't remember off the top of my head right now. But they offer all kinds of maps. So not just geologic maps, which is something worth noting. So if you're looking for any kind of map, they'll usually have it. Of course, availability is kind of determined by like, you know, whether people are actually contributing that kind of information, because a lot of these databases are based off of what people are actually researching. Like, what are people actually researching in schools and in their jobs, and what are they actually making public? But by now, you know, it's been decades. People have contributed a lot, so there is a lot available. But it's an online interactive map. It's really awesome. That being said, it takes a lot of Wi-Fi power and a lot of bandwidth because it's a lot of information to load when you're using the interactive map. But they also have versions that are PDFs that you can print. Some libraries offer like online, like you can order the printed versions online and get them mailed to you, or you can like buy the PDF and print it yourself, which is usually cheaper to buy the PDF. A lot of work has gone into making these maps, which is why they typically charge for them. But yeah, those are just some of the best ways you could like do it right now, sitting on your phone or computer, is to just USGS or your local library, or your local like even like a museum or a national park.
Cool. Excellent. I don't think there's any more questions. I just wanted to make a quick comment about one of your slides where you did the topographic like 2D map, you know, looking at a topographic map and then the 3D version of it. I think that I used to teach that in some of my wilderness classes, and I think it's a really fun way for folks to learn, like to contextualize like topography, looking at whether it's a digital map on, you know, right with GPS with whatever layers you're using. But like, I would just encourage people to use that to get context when their friends are like, so what's the elevation on this ride? And you're like, yeah, no, it's no big deal. And then you're you draw it out and it's like, it's not this gradual thing. It's actually like, boop.
We're shooting straight up all these lines. Yeah. And I think too, sometimes I tell people, you know, it gets them a little jaded or a little jostled, but sometimes I'm like, hey, you know, what are you going to do when we don't have GPS devices? What are you going to do if, you know, our phones die and, you know, stuff goes down and it's an apocalypse? Like, what are you going to do? You know, maybe not even apocalypse, but just like power goes out and you can't charge anything, or, you know, you got to be able to improvise and kick it old school and, you know, figure your way around. So having those skills are going to be real useful. Going to make you a top contender for the base camps in the apocalypse, you know.
Awesome. All right. Well, thank you so much, Alexa. We'll see you in a couple of months.
Couple months, yeah.
This is going to be a quarterly thing, so y'all that are still sticking around, We'll do a summer thing, and we'll do a winter thing, and a fall thing.
Yeah. And my tag is right here. So if you want to ask me any questions, you weren't able to watch it live, or you just couldn't think of anything quite yet, just feel free to message me. Always happy to talk rocks.
Awesome. Thanks, Alexa. Have a good night.
Thank you. You too.